I'm a principal investigator at EPFL, that's École Polytechnique Fédérale de Lausanne. This is in the Laboratory of Materials for Renewable Energy. The objective for our continued work in the direction of CO2 reduction is, of course, to expand on the ability to produce different materials and test different materials with a high rate. We need better catalysts, better materials fast in order to tackle climate change. And this paper is exactly that. The key findings for nature synthesis are the ability for acetaldehyde to be produced with a very high selectivity, over 90%, and at a very low overpotential, meaning with a high energy efficiency. The production of the catalysts, so the clusters, that they actually retain their size, they have a specific atomicity. And then thirdly, the ability for the catalyst to retain its metallicity even after exposure to air, which is not typical for clusters of this size. And that means that they actually can be reused time and again. What we're proud of is that we have now an ability to electrochemically use CO2 as a feedstock, which usually is a waste, and convert that into something that is of value by using purely electricity, water, and CO2. And we can accelerate the transition away from petrochemically sourced resources towards using CO2 now as a feedstock. With respect to traditional methods that one would use in the laboratory to produce catalysts in general, generally speaking, they are wet chemistry based. The challenges with wet chemistry is that the reproducibility of these processes is not always straightforward. And the beauty of VS particles technology is that with a push of the button, if you have generated a recipe in order to produce the particular type of material that you want to produce, if you push the button again using that same recipe, it will produce itself time and again. So you only need to optimize once and then it works. These particles, Nanoparticle Generator G1, but also the nanoprinter, I would argue, have the opportunity to really quickly iterate to different types of materials, different kinds of materials. And the speed of the iteration allows for an extension towards self-driving laboratories, and not only in electrocatalysis, but in all kinds of catalysis processes. That's really phenomenal, and I see that have tremendous impact across research in material science. Our previous nature synthesis publication took us about, I don't know, maybe 3 years of synthesis and testing in order to get an actual result. We did this now in months, and that time acceleration, you can't get that anywhere.